Hi folks, we're continuing with some Chapter 8 problems, and here goes. Doofus claims he doesn't need to put his kids into no stinking old car seats. He's very strong and he can simply hold his child and keep the child safe through any old car crash. Well, let's find out. Let's say a child has a mass of 12 kilograms. So we have a child with a mass of 12 kilograms. And if there is a head-on collision of two cars, each going 60 miles per hour, that's the same thing as hitting a wall and coming to a stop from 120 miles per hour. So the change in velocity is from 0 down to 120 miles per hour. Typical crash of this type will happen over a time frame of about 0.100 seconds. Everything's going to happen and be over in about a tenth of a second. I want to know what force will be applied to the child during this time of deceleration. Now, this is a typical, really excellent situation for the momentum impulse theorem. Mass change in velocity is force change in time. First thing, as you look at this, when we're solving for force, it's going to be mass change in velocity divided by time. And we've done that in a couple other problems. We've got kilograms, we've got seconds, we've got miles per hour. And as you know, that's not going to be pretty. We're going to have to do some converting. So first thing, let's convert that 120 miles per hour into meters per second. So let's get that done first. So let's get rid of miles, go to meters. There's 1609 meters in a mile. That's going to cancel. I like to circle what I'm keeping, so I'm done with meters. I'm going to get rid of hours, go to seconds. There's 3600 seconds in 1 hour. And now I'm going to pick up my calculator and let's see what we get. 120 times 1609 divided by 3600, and I've got 53.6 meters per second. Now that we've got that, let's put it in the momentum impulse equation. So force involved is going to be the mass of the child, 12 kilograms. Change in velocity, 53.6 meters per second, going from the original velocity of the child down to 0, and typical crash time is about a tenth of a second, taking it out to 3 sig figs, and let's see what we get. Times 12 divided by 0.1, and I ended up with, taking it out to 3 sig figs, 6440 newtons. Newtons because it should be on the top, kilograms times meters, seconds are in the bottom here, and there's another second, kilogram meter per second squared is a newton. Now that's the force on the child. The second question, part of this question, is how many g's of acceleration are imparted to the child, and remember 50 g's are considered lethal. Well, okay, how do you figure g's? Well, g's are just a shorthand way of describing acceleration. So let's go ahead and do that. How are we going to calculate acceleration? We're going to go back to our old friend F equals ma. Acceleration is going to be the force applied divided by the mass. So the force on the child is the 6440 newtons, and I rounded off, of course, here for sig figs, divided by the mass of my 12 kilogram child. So this is going to be 6440 divided by 12, and I ended up with 537 meters per second squared. G's you find by taking your rate of acceleration divided by the acceleration of gravity, and so g's are going to be equivalent to 537 meters per second squared divided by 9.8 meters per second squared. So divide that by 9.8, and I get somewhere aroundish, and yes, I'm rounding off, to about 55 g's. Lethal is basically anything over 50 g's. Yeah, I'm sorry. You're not going to, I know you want to save your children by holding on to them. Not in a situation like this. That's why car seats were invented. All right, let's go down to problem 12. A 90.6 kilogram package falls off of a truck. So we have a mass of a package. It's 90.6 kilograms. And it falls off a truck originally going 17.8 meters per second. It comes to a stop. So its change in velocity is 17.8 meters per second. It comes to a stop in a time of 8.20 seconds. What is the coefficient of friction between the ground and the package? Ooh, this is more exciting. We're coming up with coefficients of friction. All right, how are we going to do this? Well, here's what's going on. When you have a truck, here's my fancy drawing of a truck. We have a package that spills off the back of a truck, and it's then going to slide across the ground until it comes to a stop. The net force that is acting on that package is going to be a force of friction that is going to make the mass decelerate. So the only force acting on it here, slowing it over that distance, is going to be the frictional force. So if we use the momentum impulse theorem, we can do that to calculate the force of friction. So let's do that first. The momentum impulse theorem, mass change in velocity, force applied over time. The force then is going to be mass change in velocity over time. So we've got our 90.6 kilogram package. That's a pretty big package. I mean, that's, yeah, we're getting around 200 pounds. Times 17.8 meters per second. It's going to be sliding on the pavement for 8.2 seconds. So the frictional force slowing this down is going to be 90.6 times 17.8 divided by 8.2, I get 197 newtons is the frictional force acting on the package. Now what do we do? Well, if the package is sitting on the ground, the force of gravity down will be equal to the normal force up. And if you recall, frictional force is mu times normal force. So mu is going to be frictional force divided by normal force. And in this case, normal force will equal force of gravity. So my frictional force is 197 newtons. The normal force will be equal to the force of gravity. And force of gravity, as you know, is mass times acceleration of gravity. So the mass of the package is 90.6 kilograms. The acceleration of gravity is 9.8 meters per second squared. So mu is going to be, let's see, 197 divided by 90.6 divided by 9.8, and I get a coefficient of friction of 0.222. There we go. All right, we will see you later.